So normally, for example, the typical problem is that if you have an existing object, an existing part of the object, and you want to create another part, a separate part with a certain degree or level of continuity, then you basically are facing this kind of situation. So I have two curves right now, and I want these two curves to create a one single smooth path. And in order to do this, you see that now things looks like pretty good already, but they are not that good, because if you go closer, you see that here there is some kind of barely visible vertex happening. How can we adjust this? Well, in this case, for example, I can simply turn on the control point of these two lines. And as these two control points are defining the end tangent for the first line, and these two are defining the start tangent for the second line, then the only thing that I can do, depending on if the position of this vertex here is fundamental, and I cannot change it, well, eventually in this case, I will simply create a line starting from this point here. I'm going to hover with the mouse on this point. I'm not making any click here. I'm just using the tab key of the keyboard in order to block the direction defined by this snap to this point. So I can extend this line actually in this direction as much as I want, like for example, like this. And I have created a physical representation of the end tangent of my first curve. And then if I want to avoid any discontinuity, any visible discontinuity in this point, I simply take the second control point of the second curve and align it on this line with the previous two control points. So basically what I'm saying is that the end tangent of the first line is coincident with the start tangent of the second line. It means that the two curves have the same direction in the connection point, which is the definition of the first definition of, well, actually the second definition of continuity in one point. So you see that this first rule, which defines basically the tangent initial and final tangent for a curve, is already useful to create a visible continuity between two different parts. Okay, this works both with curves and surfaces, as we will see during this course. But it's very important to start understanding what you can do with control points. So I will leave it like this scheme like this, because it's the first level of control that we have on our geometry, on our NURBS geometry. We are going to discuss a couple of other rules that are very useful. So for example, we have been saying from the start today that the problem with the control point curve, the main problem with the control point curve that makes, well, plenty of users prefer the interpolated points is that you cannot define directly the passage of the curve for a precise point. So how can we achieve this kind of behavior? So how can we work with a control point curve, like clicking on a point and making that curve pass through that point? Okay, so we have just seen that two control points, initial control point and end control points, define the direction of the curve in a specific point, which is the start point and the end point. Let's see what happens, for example, if I have this line here, and I want a NURBS curve to do whatever it wants, and then simply become tangent to this line. Okay? So if I have this, I know that if I want to have this curve become tangent to this line, I need to place a couple of control points along the path of this line. So I will place one control point here and another one here, and I know that my curve is actually tangent to this line here, and it's tangent in this point, because it is the end point. Actually, is the last point that I have defined. Okay, so if I end the curve here, you see that this is the shape that I get, and my curve ends in this point with this tangent. Now, what if I start a new control point, a new control point curve, starting from this point, and I want to be tangent to the same line. Okay, so I want it to be tangent to this line, means that I have to place a second control point along this line, and then I can move away and do whatever I want. Okay. Now, if we consider this as we did here in this scheme, we are reproducing exactly the same situation. I have one curve ending in one point with one specific direction, and another one starting from the same point with the same direction. Okay. But if we could take into account both of the curves, you see that if we basically consider this particular situation here, we are saying that in order for one curve to be tangent to a specific line, then we are aligning three control points. Now, being tangent to a specific line doesn't mean that the NURBS curve is passing through a specific point. Okay, and I'm going to show you this in a while. But yes, we are defining the tangency to a specific line. So we are controlling that at least this curve touches this line in one point. So the curve is passing through one point of this line, which is already something. Okay, so we can define, for example, the passage, or well, actually the tangency to one NURBS curve to a specific line. And we are seeing that this happens aligning three control points. So this is already something that has some use for us. For example, if I have let's say, a region in our plane, but it can also be a 3D region, right? If we have a region in our plane and we want to draw an organic shape inside this region without exiting this region, then we must take into account this second rule that we just saw. By aligning three control points, we become tangent to a specific line. So for example, if I start drawing something like this, and then I want to be tangent to this line here, I just turn off the center snap because it's quite boring. And I just click on 1, 2, and 3 points along this line. And I am touching the line without passing through it. Okay. Then I can do whatever I want, and then I can align 3 control points along this line, and I am touching the edge without going through this. Okay. And I can do this as many times as I want. The fact that I am taking 3 points in a row along these edges here is enough to avoid that this line comes out from this perimeter here. Okay, and then I will close it simply, okay, because it's more than enough. So you see that I can take this rule and take advantage of it in order to create this kind of particular geometrical condition. Okay. What's the advantage of doing this is that if I take this control point curve and I click on it with Rhino 6, I already have the visibility of the control points, okay? And so I can edit the shape of this curve because I have created the necessary topology in order to have a curve tangent to this perimeter here, okay? So the control points are placed exactly in a way that allow this curve to be tangent to the outline. So if I take this control point here, I know that if I move this control point along this edge, I am not breaking the tangency between the curve and the line, okay? Because I am always keeping the 3 control points aligned along this edge, okay? So if I see, for example, that this thing has become too, I don't know, weird, in some point, I can regularize things like taking this point and move it along the line, and I'm not breaking the rule, okay? So the advantage of working with a control point curve is that you don't define the shape. You define the geometric properties of that shape. And as long as you maintain the geometric property untouched, then you can change the shape however you want. And you can always have a different shape respecting the topological rule and geometrical rule that you were considering. Okay? So, for example, if I want to create a curve which is tangent to this area of this polygon here, I can also create a curve like this. I want this curve to be tangent to this line. Well, I need 1, 2, and 3 control points. I want tangency to this one, so it's another 1, 2, and 3 control points. Tangency to this one is another 1, 2, and 3 control points. Okay, and so on. And I can work however I want, and I can close the shape. So I am creating the necessary topology to create the geometric condition that I want. And once I have created the right topology, I simply take the points, move them in position, in order to create the final shape or the, let's say, approximate shape that I eventually need for my curve. You see? So another 3 control point here. And then let the rest of the curve behave as it wants, okay? But I am sure that this curve never passes through the edges of this polygon, okay? I told you that this is not the same as defining the passage through a specific point. We are defining the passage tangent to a specific line, okay? So this can actually be useful if you want to control the general geometric properties of this line with respect to another one. But let's say that I want a NURBS curve to pass through a specific point. Now, um, how we can do this, okay? So I am drawing a freeform NURBS curve like this one, and then I want the curve to pass through this point. Passing through a point is a particular case of being tangent to a line. So I want this curve to be tangent to a virtual line, and I want to be tangent to that virtual line in a specific point. Let's see it like this. So I always need 3 points that I can align, okay? And then I want this curve to do whatever it wants, okay? So I have these 3 points that I can use in order to define the passage through this one. So how can we proceed? Well, in this case, I will take the mid control point and place it exactly in the passage point, okay? And then I need to align these other two with this one. So eventually what you can do in order to speed up this process is take these 3 points if you want. Well, actually, take these 3 points here and use the set point command, which is this one, set XYZ coordinate, which is the set point command. And, well, I don't know, you can choose between aligning X and Y, whatever you feel more comfortable. I will pick Y in this case. And I am aligning these 3 points in their horizontal direction, okay? And then I take these 3 points, move them in order for this point to be coincident with this one. So we are already defining this curve, tangency, according to this horizontal direction, okay? But if I draw this line, for example, a line between this control point and this control point, and take a closer look, I see that the center, the mid control point, is not actually the point of contact between this NURBS curve and the horizontal line. The point of contact happens somewhere here in this area. You see that now the curve is separating once again, and here is separating once again. So the point of contact happens somewhere here. And I don't know if you already can guess what point this is for our NURBS curve, but this is a knot, okay? So when I align 3 control points in a row for my NURBS curve, the contact point between the NURBS curve and the tangent line is a knot. So how can I make our NURBS curve to pass through exactly through this point here? Well, in order to do this, I simply have to make these 3 control points here symmetrical with respect to the mid control point. So for example, if I take a circle from this point and give it the radius that I want, okay, it doesn't matter actually, and take the control point of my line and place this control point in this intersection and this control point in this intersection here, I am creating a symmetric set of 3 control points, okay? And this means that the relative knot actually lies with correspondence to the center control point. So actually, if I want this curve to pass through a specific point, what I need to build is this kind of situation. 3 control points in a row with a constant separation between them. And in that case, the curve will pass through the mid control point. And this is actually what is happening here, okay? So in this case, I know that if I want to work with a NURBS control point, I can force the curve to pass through a specific point by aligning 3 control points and keeping a constant separation between them, okay? So knowing this, we already know how to work with a NURBS curve which has a specific direction at the start and end, and also that can pass through a specific point. The only thing that we miss with this NURBS curve is that, but actually we can reproduce the behavior of an interpolated points curve using just these two simple rules, okay? And we can be more precise because we cannot, for example, use an interpolated points curve like in order to define the initial direction. Because if I click this point, you see that the curve starts from the start point and reaches the second point. But if I move away, I am changing the initial direction. Okay? Then I cannot use the interpolated point curve in order to create a specific continuity condition, for example. There is no way that I can do this. Okay? While with the control point curve, we can define the position, the exact position of the second control point that will remain in that position. So the shape of the curve might change during the creation of the curve itself, because if I start, for example, a control point curve from here, and I set the second control point here, the third control point still affects the shape of the curve at the start point, okay? But not the direction. The direction stays untouched, okay? So with the control point curve, we can control exactly the not only the shape but also the geometrical properties with relation to other geometric entities in our drawing. Okay, so the last thing that we must define, for example, with a NURBS curve is how can we, for example, define a straight segment using a control point curve. Now, of course, we can lower the degree, right? But I'm not talking about a polyline. I'm talking about an organic shape like this one that suddenly has a straight behavior or aspect, and then goes back to an organic shape, okay? All in one single line, not like drawing a NURBS curve and then drawing a straight line with a polyline and then another NURBS curve segment and then joining all together, okay? I want to do this only with one single NURBS curve command execution. So let's consider once again this situation, because we are basically taking it as a start. Let's say that we want, between this curve and this one, we want a straight segment. So the only thing that we can do, that we must do here, is take this, eventually copy it, so that its start point lies somewhere like here. So if I consider this and this, you see that it's like defining a first part of the curve, like ending here. In order to end here and have this tangent, I need to define the position of this control point and this control point here. So these last two control points define the final tangent for our line, which is aligned with this one, with this tangent line. And then I have the second line starting from another point, and with the second point aligned here in order to have the same tangent. Now, if I consider this sequence of 4 control points, what I would do if this was one single command execution, by aligning 4 control points, I am defining this tangent here for this final segment, and then I'm starting on the same tangent, defining the same tangent, but on exit, right? What happens in between? Well, the curve only has these 2 control points in this area and these 2 control points here. So the only thing that it can do in between these 2 control points here is basically maintain the straight direction, okay? It cannot bend anyway, because there is no control point inside that can allow bending, okay? So basically, what we must do in order to have a straight segment or a straight portion of our control point curve is align 4 control points. So you can see that, for example, if I have this straight line here as a reference, I can draw whatever I want, and then place 1, 2, and then 3 and 4 control points, and you see that my line is actually having a whole section which is totally flat. Where is this flat section starting and ending? It is not starting in the control point that are between this set of 4. As you go closer, you see that there is separation here, and there is also separation here between the lines. It is starting in the correspondent knots. Okay, so as always, the knots define the passage between one span and another span. In this case, we have a span which is totally flat here. So the span we are talking about is contained between two specific knots, okay, and not control point. Of course, the control point position affects the position of the knots, because we know that there is a strict relation between control points, knots, and degree, okay? So, of course, if I change the position of the control point, I will affect the straight portion of my line. But, for example, what I would do eventually, in this case, is get this point closer to the first one, and get this point closer to the second one if I want a longer flat portion. Or I can, let's say, move them closer to each other if I want this flat portion to be like more short, basically. Okay, so I can always control via the control points what happens with my with the shape. Okay, but I am creating the right topological condition in order to have a flat portion of my line. Okay, now all that we are saying here, these are what I call the three basic rules for NURBS curve definition. So initial and final tangency, and passage through a point or tangency along an internal point of our NURBS curve, and flat portion of a NURBS curve. With these rules, you can basically create whatever type of condition that you might want to create. For example, and we will discuss this later on when we will be working with surfaces, for example, but many people tend to do something like, okay, I need, for example, to draw a rounded rectangle, okay? Now, in order to draw a rounded rectangle, there are several workflows that you can adopt. The first one is creating a rectangle and specifying you want the rectangle to be rounded. So after creating the rectangle, you are allowed to round up all the vertices at once. Or you can create the rectangle like this, and then you can use the fillets. There is a fillet for a specific vertex, or a fillet corners that allow to fillet all the vertices of a polyline, which is basically the same. And I can fillet this with, I don't know, a radius of 2, and I am rounding all the corners at once with the same radius, which is something that is very useful in mechanical design, for example. But there is another option now, and this option is, well, depending on the type of result that you want to achieve, but this option gives us a totally new look to, let's say, this kind of problem. So I could create, for example, a NURBS curve using this rectangle as a reference, okay? Like this, for example. I will create a starting point here and another point here. And I need 4 points in a row to have a straight segments along this side. So I need to place 1 point here and another point here. So I'm moving in this counterclockwise direction. So I will place a control point in the vertex. Then I need 4 control points along this side to have a flat side. And then I need, this is the first one, and then I need the second one, third one, and fourth one. And another time, first, second one, third one, fourth one, second, third, fourth, and then I simply close the curve. What I get here is a rectangle which has some rounding happenings at the corners, but this is not the same rounding that we get with the fillet. It's a different type of rounding that we can control, of course. We can make it symmetrical, for example. We can create a circle here with the radius that we want, like, I don't know, something like this. And then we can take the control point of our NURBS curve and place them in the intersections. No? Okay, like place this in this intersection and do the same for the other corners. Now, this type of rounding that we are getting here is totally different from this one, because the fillet creates an arc, basically. It's a portion of a circle. While in this case, we are working with a NURBS curve, a degree 3 NURBS curve, and we are working with internal control point. So this situation here is more similar to what happens in this area than what happens here. even if here we don't see any vertex, the level of continuity that we have between this straight line and this arc is not the same level of continuity that we get inside this segment of a NURBS curve. This NURBS curve flows smoother than this one. And this is what happens, for example, here. Okay, so what happens is that eventually, if I use this version of a rounded rectangle to create, I don't know, something like sweeps, extrusions, and so on, then I will get a more continuous surface than by using this kind of geometry here. We will discuss this later on when we will be dealing with surfaces, but we are starting to talk about another topological aspect of NURBS geometry, which is continuity. Okay, and it's very important to understand how continuity works, because this not only affects the continuity between different objects, but it also affects the continuity inside one single object. And we must know how to define the proper continuity level in order to obtain normally the simplest result possible, because this will affect all the workflow. If you get to the simplest result possible, you always have a smoother workflow when working with Rhino. So that's why the title of my book is Simplified Complexity. The goal is always to get to the simpler result, okay, in order to simplify all the workflow. So what we are going to do right now, I'm going to delete this because it's well, it's just an introduction to what we are going to do right now. And I'm going to save this scheme here. I'm going to shrink it a little and move it apart. Okay. So let's take a look at what happens in terms of continuity when we work with control points. Okay, let's see what we can do in terms of continuity when working with control points. And on the other hand, let's see what we can't do in terms of setting continuity working just with direct control point modeling. Okay, so
Giancarlo, the point transform point command wasn't inside the transformation toolbar. Just a quick question. The one X, Y, Z.
No, it's a transform command. It's a transform utility, so you can find it inside the transform toolbar,
and
it's here.
All right, that's it. Thank you.
Okay, it's very useful, by the way. We will be using this quite a lot when we will start working with surfaces. Okay, but yeah, it's very useful. Actually, I don't know if I didn't put it in my custom pop-up toolbar, but yeah, it's very useful. Okay, so let's switch back to our NURBS curve. We saw that there is one particular rule that we saw, the first one, that allows to define the tangency for a freeform NURBS curve with respect to another line. Okay, so let's say that we are working with a composite object. This is the first piece, okay, and we want to create another piece of the same object, starting from the same point, and initially we are going to create it like this, okay? So it's evident that we have a discontinuity here. Now we must understand what's the meaning of continuity in a NURBS geometry tool like Rhino, okay? Because the common definition of continuity for geometry, for example, is the intuitive definition that says, well, two lines basically are continuous if you can draw them without, let's say, disconnecting the tip of your pencil from the paper you are using, right? So basically, two lines are continuous if there is a continuous flow between one line and the other one, despite the fact that they are creating a vertex like this. Okay, so there is some kind of continuity between these two lines. Of course there is, but this is not the kind of continuity that we want, because normally Rhino has become the standard in product design, for example, exactly because of this possibility of avoiding creating visible discontinuities. Okay, so for example, let's say you want to create a fork, which is a very complex object, right? Of course, it's almost impossible, unless you have a perfect knowledge of topology, to create a fork with one single surface, okay? But it is possible. But the average user, or also the professional in that case, tends to create that kind of object using a polysurface. So several surfaces connected together. And the thing is that you don't want creases, visible creases along the surfaces. You want the object to appear as smooth as possible. So one thing is talking about continuity, and one thing is talking about smoothness, okay? We don't want just continuity in Rhino. We also want smoothness, okay? So this is continuity already, but it is not a smooth continuity. So what we can do with control point, direct control point modeling, is placing the second control point here in a precise position, or well, along a precise direction, in order to avoid the presence of a visible vertex. Okay, so we know that we can select this one as well, and we can create a line, for example, tab on this one, and then place this point along this line, and that's it. We already have an invisible connection point here. But in terms of continuity, this might not be enough. Okay, so let's go back. This continuity here in Rhino is called position continuity. Okay, and it's called so because basically the position of the endpoint of one body corresponds to the position of the first point, the start point of the second body. Okay, so it's just a contact continuity, position continuity, and it is schematically named with the G0. Okay, so let's say the nickname of position continuity is called G0. So we have G0 here, continuity. And when we do this, we set tangency continuity, which is called G1. Okay, so G1 is the lowest level of continuity we need in order to avoid the presence of vertices in the connection point or along the connection edges between surfaces, or connection point between curves. So G1 is the lowest level of continuity that allows avoiding visible discontinuities. Okay, but this might not be enough. And I'm going to exaggerate a little right now. So what I'm going to do, I'm going to move all these control points away like this. And what I'm going to do right now, I'm going to take this control point, and we saw that control points are basically defining the general properties of a curve and the general topological property, but also they affect the general geometric behavior and relationship with other elements. So in this case, these two control points here are saying that this second curve must touch the first one and must be tangent to the first one. And tangency is not given by this specific position of this second control point. This second control point can slide along this line. And I am getting a set of different tangency options, but I am not breaking the rule. So each time I move this along this line, I never create a vertex in this connection point. But what happens if I take this point and move it closer and closer and closer to my connection point? See, I'm zooming in and getting closer and closer and closer. If I still zoom in, you see that I am still tangent. I am reaching the graphic capabilities of my graphic card, okay, which is quite powerful. But you see that when you start to see this, it's because the graphic card cannot handle this type of precision, okay? It's not a geometrical problem. It's a visualization problem due to the graphic card, okay? So I will move away, but you get the point, right? This curve is still tangent to the first one. But sure, but what happens if I go at the scale of the object? I don't care that there is no vertex here. Still, if I, for example, fall on this point of this curve, and I can still get hurt, because this is evidently this is a vertex. Even if it is not a vertex, at a macroscopical scale, this is actually continuous with tangency continuity. But at the object scale, this is a vertex, right? So this is what happens, for example, when you think about a needle. So the needle is extremely sharp, but if you look at it under the microscope, you would see that it is not sharp at all. Okay, so we have a problem here because G1 continuity it might be enough for a whole bunch of applications. Normally, for example, G1 continuity is more than enough for architectural design, okay? Because in architectural design, it's very unlikely that you have sudden change of direction in your surfaces or your lines, okay? Because you're working at a large scale. And the level of detail never reaches very, very fine details. But if you work, for example, like in product design, in mechanical design, jewelry design, where you have to consider very fine tolerances, then in that case, yes, G1 continuity might be simply insufficient for creating the proper geometric condition. So what comes next? Well, G0 is position continuity. G1 is tangency continuity. The next level is G2, but G2 is it's quite a complex level of continuity, which is called curvature continuity. Okay. Now, the problem is that from G2 up, you have no possibility of creating this kind of continuity working directly with control points. Okay. And I'm going to show you this with another tool. So what I'm going to do, I'm going back to my first scenario, which was basically this one. And I'm going to physically disconnect these two lines in order to create a physical separation. By the way, this is called G-1, which means physical discontinuity. Okay, so when you see G-1, it means that two curves or two surfaces are simply not touching each other. But this is an extremely nerd stuff, okay? So discontinuity is discontinuity. You don't need a name. But anyway, so this is G-1. And in order to visually understand what's the problem with placing the control point for higher levels of continuity, like from G2 up, I'm going to use a specific tool in Rhino, which is one of the most important tools, which is the adjustable blend. Okay, the adjustable blend is a connection tool, which is similar to a fillet or a chamfer or whatever. It creates connection between lines, right? But it creates a connection in an adjustable way. So let's see what this means. You must select a curve, start curve to blend, which is this one, and the second curve to blend, which is this one. And we start to get this connection line here. Now, this connection line is quite a complex line. It is based on the general properties that you adjust in this interface here. This is the interface for the adjust curve blend, right? And you see that there are two columns. First one, named 1, refers to the first curve you have selected. In my case, this curve here on the left. This dot here is basically naming the curve, the connection point along the curve that corresponds to the first column. Okay, it's the first curve that we have selected, and the second one is this one, and the second column corresponds to the second curve. So you can define several types of continuity in both ends of the blend curve that you are creating, which is only this one. Okay, so this curve is being created considering the level of continuity that you want in the endpoint of curve 1 and in the endpoint of curve 2. So we can clearly understand what's position now, because we can see that if you want the adjustable blend curve to have a G0 continuity with both curves, the only thing that this blend curve must do is start from the endpoint of the first one and end in the start point of the second one. And in order to do this, there is no need for additional complexity, because you only need a control point here and a control point here. And so the result is going to be a straight line with two control points, which, by the way, is going to be straight and linear. Okay, because straight because of the shape, linear because if we have a control point curve with just two control points, the degree of this curve is going to be 2 minus 1, so degree 1, which is a linear equation. So we have a straight connection with degree 1, straight and linear, right? Which is the simplest connection possible. In the moment I increase the level of continuity that I want, at least in one of the two ends, like tangency in one, you see that Rhino creates two control points because it needs the first control point for the start point and the second control point to define the tangent. Now, this point here is aligned to the control point, the previous control point along the path of the first curve. Okay, so this direction here, you see this continuous line here is defining the final direction, the end direction of the first curve. So it's the end tangent. Okay, and as well, if I do this on the column 2, the same thing happens in with corresponds to the start point of the second curve. So this is automatically doing what I was doing by hand, creating a straight line as the continuous line with respect to the final tangent to the first curve, and placing the second control point along that line. This is doing it automatically. Now this is adjustable not only because you can adjust settings here in this window, but also because you can edit the control point position. So if I click on this point, I can now move the mouse and move this control point away or closer to the connection point. And you see that I cannot move this point away from this direction because this is defined by the tangency condition. So this point is forced to stay on that line, virtual line, okay? But this means that I can create a whole set of different blend curves respecting the topological tangency condition, which is, by the way, something that we already discussed when we were working with all of these examples here, okay? You can simply change the shape of the curve without breaking the geometrical rule, which was being tangent to a specific line, by sliding the control point along the tangent line, which is something that's happening here automatically, okay? And I can do this for both ends of the blend curve. Now, so there is no difference from this that we are doing here dynamically inside the adjust curve blend and what we did before by hand by tweaking the position of the control point. What happens when I decide to switch to curvature? Now, curvature needs 3 control points, but these 3 control points are impossible to place by hand. Let me do another tweaking because here it might seem that we have 3 control points aligned, okay? So I'm going to slightly change the shape of these 2 curves in order to get to the end point with some curvature, because you see the curve is almost flat, you know, where it reaches the end point. So I'm going to create some curvature here, okay? And then I'm going to repeat the adjustable curve blend between this one and this one. So if I want curvature continuity, you see that now we have 3 control points, and these 3 control points are placed in a very, very specific position. So you see that we always have start point and end point. We always have start tangent point and end tangent point, which is the second control point. But then there is a third control point. And this third control point is not aligned with the previous 2, not in the first end, not in the second end, right? And these 3 control points, if you have some imagination, you can see that if you imagine a line, a NURBS curve that starts from here, ends up here, and have these intermediate control points, the result will be an arc. These 3 control points are basically symmetrical with respect to the center control point, okay? They have some angle here. If they are 3 control points, they would create a degree 2 curve. The arc, being part of a circle, is a degree 2 curve. So these 3 control points here are defining exactly the control polygon for an arc. This arc represents the curvature of this first curve in the end point, okay? We are going to see this in detail later, but I'm going to just show you why it's impossible to place these 3 control points by hand. If we consider this, we should, imagine doing this by hand, by placing directly control point for a new NURBS curve, okay? Of course, we can place this. eventually we can place this more or less as at the correct distance, okay? But there is no way that we can place this by hand, because we don't know what's the relation between these three control points and the radius of curvature of the arc that we would eventually create by placing these three control points. So it's something that is not intuitive at all, okay? And moreover, take a look at what happens, for example, if I tweak the position of these control points. If I move this, the third control point moves accordingly, because it must maintain a symmetrical set, because it needs to create an arc. But this is no surprise, right? If I move the center control points, the third one is simply symmetrical with respect to the center of a virtual a curvature circle, which we will be discussing later. So you can see what's the relation between these 3 points if I move the second one. But what if I move the third one? And you see that the second one can only move along the tangent line, of course, right? So there is a strict relation between these 3 points. But what if I move this one? And if I move this one, things start to be somehow very, very strange. Because actually I am breaking the symmetry between the 3 points. I see that this point is forced to be moving along a specific line that I don't know. I don't know why is that one. I cannot simply imagine that there is this straight line forcing the point to move along it. So it's impossible to understand where do I place the 3 control points by hand in order to have curvature continuity. So in order to achieve curvature continuity, so G2 continuity, the only thing that you can do is use this command here, or other commands that are always inside this toolbar, like for example the match curve and so on. Okay, but you cannot do this by hand, right? So this is the problem with direct control point modeling. You cannot automatically set the proper continuity. But what you can do is set the proper amount of control point that can be used by Rhino in order to adjust the right level of continuity. I mean, if I need to create a connection line between these two here, and I need this connection line to have curvature continuity here and curvature continuity here, I know that this segment, this line, must have at least 3 control points for curvature continuity here and 3 control points for curvature continuity here. So what I can do is take a control point curve, make it start from here, eventually, but it's not mandatory, eventually place the second control point aligned with the tangent to the first line, but it is not necessary. And I need first control point, second and third, and then I need 1, 2, and 3 control points. By drawing this, no matter where I place the other control point, it's absolutely irrelevant, okay? But I have the right topological structure in order for Rhino to edit the shape of this curve and create curvature continuity in this connection point and in this connection point. We will be discussing this later when we will deal exactly with the continuity. Eventually, we will do this directly with surfaces because it's way more interesting. And it's basically a two-way scenario. We are seeing things in working with curves that are exactly the same with surfaces. And we will see things in surfaces that can be simply applied also with simple curves, right? Because in the end, everything is based on NURBS equation, both curves and surfaces. Okay, so what we are discussing here is also valid for surfaces. And what we'll be discussing in surfaces will also be valid for curves. Okay, so I can work with control point, direct control point modeling. In this case, I cannot define exactly the precise continuity level from curvature up. I cannot do this. So I have to use utilities, which are, by the way, blend curve, match, and so on. But I can provide the right topological structure, meaning the right amount of control point in order for this curve to become that tangent to the existing ones, okay? So, by the way, in this case, the more intuitive way of creating this connection line with curvature continuity would be to create an adjustable curve blend with curvature, okay? So you might see, for example, that these 3 points are basically taking the shape of an arc, which has the same curvature of the curve in this endpoint. Okay, so you can imagine that in this case, for example, concavity of this arc is going to the left because this curve has its concavity oriented to the left, while here it is going to the right because this concavity here is facing right. Okay, so it's intuitive. We will discuss this analytically later on. Okay, so there are the only direct control that we have over continuity when working with the control point curve directly is over position continuity, so G0, and tangency continuity, which is G1. I repeat, for architectural design, for example, this is more than enough to define smooth shapes, okay? Because in architecture, you have no sudden direction variation, okay? In mathematical terms, we are not going to discuss this from a differential equation and differential geometry for curves, for example. We are not going to discuss this in mathematical terms, but you can think about position continuity is basically saying that the endpoint of this curve corresponds to the endpoint of this one. It means that basically the equation of this curve starts where the equation of this one ends. So this is position continuity. And it means that the two functions have the same value in the start and end point. Okay? Tangency continuity means that the first derivative to this curve in the endpoint is equal to the first derivative of the second curve in the start point, because they have the same tangent. And the tangent is the first derivative of the function of a curve. Okay? Curvature is the second derivative. Okay? So it's the derivative of tangency. And so curvature expresses the variation of the tangent along the curve. Okay? As tangency defines the variation of the shape of the direction, the curvature defines the variation of the tangency. In what kind of design you should work with G3 or G4? This is very interesting because G3 and G4 are basically, they also have a funny name in terms of derivatives, because if G1 is basically defining the direction, which is tangency, then there is G2, which is curvature, and then there are G3, G4, G5, and you can go up to G whatever you want if you think about it, okay? Because as long as your equation allows first, second, third, fourth, fifth degree derivatives, then you can go on and on and on and on and calculate this new function, okay? Let's go to a practical scenario, right? So we are working with degree 3 curves, okay? Degree 3 curves means that you can have first derivative, which is going to be a degree 2 function. Then you have second derivative, which is going to be curvature, which is going to be a degree 1 function. And then you have, after curvature, there is the derivative will only result in a constant value, which means that G3 has no variation in our case. In a standard Rhino workflow, there is no need to consider G3 or G4 or G whatever. Now, think about this in geometrical terms, because if you go into calculus, it becomes very difficult, right? So what I'm going to do right now, I'm going to draw something. Oh, no, we can actually use Grasshopper in order to perform this kind of analysis, right? So what I'm going to do right now is take this line. Let me place here. Take this line, set one curve. Right, so we have this curve in Grasshopper. And if we go into curves analysis, there is a whole set of things that are here that is meant to calculate or to perform a detailed analysis of this curve. This is something that eventually, I don't know if you attended the webinar that I gave a few days ago on NURBS topology, introducing this course exactly. Where there was a Grasshopper definition, which is, by the way, actually it is, I think it's available in the description of the tutorial on my YouTube channel. But we are interested here in understanding what's the analytical property of this curve. right? So the first one that we might want to do is analyze derivatives. Well, it's not the first one because this is already something quite advanced, but you get the point. So I'm going to take this. Another time, this is a parametric component. Parametric means not that it's parametric because it's in Grasshopper. It is based on the parametric representation of the curve. So we should know what's the parameter value in a specific point, which means we should know what's the domain of this curve, right? But we don't know the domain. This is typical Rhino scenario, okay? I have this curve. I don't know the domain. I'm not interested in the domain also because if I take this value here, this is an approximation, okay? Nobody said that my domain ranges up to 51.82119. It can also be 189 or 889, who knows, right? This is an approximation. So I will never be sure that the parameter for the endpoint will be exactly that value that Rhino is saying, okay? So that's why it's better to reparameterize the line and use a normalized slider between 0 and 1. So bypass completely the domain information. That's why I was saying do not concentrate too much on knots as a value, because you will always be reparameterizing lines, okay? So I have this, and I have this moving point along the line. Let me place in a segment where in an area where there is more curvature, right? Because this that we are seeing is the first derivative, which is tangency, right? So we get the evaluation point, which is this red dot here that appears, and then we have this. This is the direction of the curve in this point, so the tangent line, which is the first derivative. And I can add also the second derivative, which is this one. This represents the curvature. Now, these represent the curvature in terms of vectors, right? Now, don't think about the curvature, this vector, as the radial direction of the curvature of this curve in this point, okay? It's not like that. Is only the vector representation of the curvature, okay? And you can also go to 3, you can go to 4, 5, 6. You can see that 4, 5, 6 are actually coincident in the point because they are null, okay? So you have a degree 3 equation because this is a degree 3 curve, right? And you have first derivative, which is an equation in general with degree 2. This has degree 1, and 3 is constant, okay? This is a constant value. Think in terms of function, right? We are just giving a visual representation of these 3 value, and I needed this in order to understand that 4, 5, and 6 are irrelevant. Remember that first derivative is g1, g2, and we are already getting a g3, which is constant, okay? Now, so let's get rid of 6, 5, and 4. Let's concentrate on g3. When g3 becomes useful, I'm going to put it like this, okay? If 1, which is tangency, represents the variation in the direction of the curve, okay? 2 represents the variation in the tangent direction of the curve. 3 represents the variation of the curvature of our line, right? Now, why is this so important? Now, I used to explain this with a metaphor, right? I assume that you all have a driving license, right? And you drive. So let's say, for example, that you are driving along a road, and this road is perfectly straight. Well, not like this because I'm driving with a mouse, but it's perfectly straight. And then you have a curve like this one, okay? Imagine, because this is not the case, but imagine that this is a constant radius curve, okay? So it has a center, and it also has a radius of curvature, right? Now, from here, to get from here to here, with a specific speed, which is, by the way, represented also by the tangent line, which corresponds to velocity, okay? Let's say you maintain the speed constant, right? If the speed is constant, in order to drive along a constant radius arc, which is a constant curvature line, you must turn the wheel to the right a little and keep the wheel with that angle constantly, right? And you will get from point A to point B with one single smooth arc curve, right? This is if you keep the radius of curvature constant, which means, by the way, having the curvature constant, right? In that case, if you have curvature like constant, it means that your variation of curvature is simply zero, right? So if there is no variation of curvature along this line, then it means that the G3 is equal to zero because there is no variation, okay? But normally what happens is that when you drive along this kind of road with this arc shape, what you do is turn the wheel to the right a little and tend to do something like this. And then you turn the wheel to the left and tend to, I am exaggerating, right? You are not drunk, but anyway, you tend to do something like this, okay? You move along this path with some kind of oscillation. This is a variation of curvature because from here eventually you start with this radius of curvature. But then in this point, your radius of curvature is more likely to be very small. And in this point, your radius of curvature has changed so much that you also changed concavity, right? So in this case, G3 is expressing this kind of variation. So G3 is very useful in a very specific type of design where aerodynamic is very important. Now think about this line here, uh, not as the trajectory of your car while you're driving a little drunk, okay? Think about this line as the surface of an object, right? More specifically, think about, for example, the surface of a car, right? So I have the front part of the car, and then I have the hood, then I have the part of the windshield and the top and so on, right? So if I have this smooth line, the variation of curvature is also smooth, right? So there is no, but basically there is no oscillation because this curve tends to be very smooth, right? So what happens if I don't have a smooth behavior of the curvature? So I have variations of curvature along these areas, for example. It means that at this scale, let's do something like this. At this scale, my surface could do something like this. What? If the surface does something like this, it means that the wind or the air cannot flow directly on the surface. It flows in general, but when it goes very close to this surface, it does something like this. And if it does something like this, it also does something like this. So it creates this kind of twirls or twisting, no, in the airflow. And the effect of this movement here is something that pulls the car backward. Okay, so this airflow like this is basically avoiding the car to proceed forward, to move forward. And so you have to push the accelerator more in order for this car to advance faster or to keep the same velocity. And you are wasting money, basically, more money. This is the famous CX component, which has to deal with aerodynamics, okay? So in this case, for example, in automotive design or in, I don't know, whatever industry that has to deal with aerodynamic, okay, or fluidodynamics in general, like, for example, ships design, boats, or airplanes, or spacecrafts, or whatever you might think about that has to deal with aerodynamics, then continuity up, also higher than G2, from G3 and above, they become important. Okay, so you see that continuity it's very, very important. But we must also deal with the standard Rhino workflow. Okay, so if you work with some problematic shapes like the hull of a boat, for example, in that case you might want to to adjust the continuity to a very detailed level. Okay, we will discuss this later on. We will discuss, for example, some basic surfaces like the loft surface and so on. And we will see what's the best thing that we can do in order to consider the proper shape of the surface without going too deep into continuity analysis, right? It's a common mistake to think that well, you might have heard about, for example, class A surfaces, right? Now, many people think that you cannot create class A surfaces in Rhino, for example, but it's not like that. You just simply have to know what's class A surface. Okay, many people simply doesn't know the meaning of class A surface. Okay, so class A surface is a surface which is continuous enough. Okay, there is no other definition. Okay, it's continuous enough. Now, you know, right now, after all this discussion here, you know that continuous enough has to deal with several things. It has to deal with the distribution of control points. It has to deal with the knots vector. We will discuss this later on. It has to deal with the degree of the curve. We know that a degree 5 curve is smoother than a degree 3 curve. We also know that there are some problems in that case, but it's not that those problems cannot be bypassed. Okay, you can also work with degree 5 curve as long as you stay inside Rhino. But you also know that if the degree of a curve is 3, you cannot have continuity level higher than, for example, G2. Okay, because G3 is already being constant. Okay, so it's absolutely nonsensical, right? If you have a degree 5 curve, it is smoother, and you can also tweak the continuity of that curve to a higher level, which can be G3 and G4. Okay, so it's a complex set of information that you must take care of at the same time when you are drawing something. So yes, you can create class A surfaces in Rhino when you work with aerodynamic surfaces, for example. You just have to know how to do it. And you have to know how NURBS topology and NURBS geometry works, okay? So, well, let's say turn this, well, let's simply skip this thing. I'm going to delete the drunk, delete the drunk curve scheme. And let's go back to our analysis here. So when you want to create some higher level of continuity, which in our case is already G2, okay, then you cannot do it by hand, by simply tweaking the position of the control point. You must work with some utility tool in Rhino. And utility tool in Rhino means, for example, that I have a line like this, which is a degree 3 control point curve. I am sure that it's degree 3 because I have created it with 6 control points, okay, which is higher than 4. So eventually I have a control point curve with more than one span, okay? So degree 3 with 4 control points is a single span curve. 5 control points means we have 2 spans. 6 control points means we have 3 spans, okay? So each control point adds a knot and therefore adds a span. We will see this also in detail later on when we will discuss surfaces, okay? I prefer to do this with surfaces because it's more relevant. So what I want to do, I have this one, and I also have a control point curve, which is going to be something like a 1, 2, 3, 4 control points, okay? And I'm going to be very bad right now, but I want a third control point curve, starting from here, doing whatever it wants, okay? And I want this control point here curve to be tangent to this one, okay? So let's say that this curve has this tangency. I want to make sure that these two curves doesn't form any vertex here. So I take this construction line here and place this point on the path of this line, okay? So I'm sure that now there is no vertex in this point. Now what I want to do is create curvature continuity between these two curves, okay? And I'm not going to use a blend curve, because a blend curve would create an additional segment here, which eventually, if I use curvature continuity, will do something like this, and then move away this side, and then connect to this other curve, okay? So if you want to see it, the blend would create something like this. You see, I was exaggerating, but this is the shape, okay? I don't want to do this. I want to connect these two lines with curvature continuity, okay? Now, remember, and I'm going to take this curve here and visualize its, sorry, its control points. Okay, so I have them constantly visible. And I'm going to internalize this line so that when this changes, I will always maintain this structure of control point and the visibility of this red line, the original line. So what I'm going to do right now, I'm not going to use the blend, because the blend creates an additional segment. I'm going to use the match curve, okay? So match curve is another utility that allows to adjust the continuity between two lines. So first, it asks for the open curve to change, okay, and pick near the endpoint you want to move or change, right? So I want to change this curve here towards this endpoint to adjust it to this line. So I pick this line here. And then it asks, select open curve to match, pick near end to match. So I don't pick this point, because else this curve will be put in relation with this curve on this endpoint. I want this connection to happen here. Now, this is the match curve command interface, and you see that match curve continuity affects the continuity between the two endpoints that I was considering. If I take into account only position continuity, you see that this curve simply stretches so that the endpoint moves to the endpoint of the other curve, okay? This is something that, well, we already know this, no? Okay, it was going to happen. What I'm interested in is not only the deformation that occurs on this curve, okay? What I'm interested in is in what I can do with this topology in order to match this curve to another one. Because if I set continuity to position, I can decide what I can do on the other end. The other end is the other endpoint of my curve. And my curve was tangent to the third one. I don't want to lose this kind of continuity. If I don't want to lose this kind of continuity, as I am editing a NURBS curve with one single span, it means that this point here, by moving this point from here to here, I am changing the whole shape of my curve. So this deformation here that you see, this switching between this yellow line and the black line, is affecting all the span down to the end point. And even if there is a very, very small deformation occurring here, I am losing tangency in this point. Okay, is it clear? So in order to preserve the other end geometrical relation that I want, I must switch from position to tangency. Now, switching from position to tangency, it means that I have a 4 control points curve. And I am telling Rhino that in order to match this curve to this endpoint here, it must use 1 control point for position here and 2 control points for adjusting tangency in the opposite end. And this is possible because I have 4 control points available. So I can match this curve to be in contact with the opposite curve here and still be tangent to the second line that I have here on the right. I can also tell Rhino, tell the match curve that I want tangency, tangency, because I have 2 control points used for the first tangent here and 2 control points used for the second tangent. What if I want this curve to be curvature continuous here and tangency continuous here? If I switch from tangency to curvature along the continuity endpoint, preserve other end set to tangency means that I am changing the topology of the resulting curve, right? So in this moment, Rhino is automatically changing the topology of the connection line. okay, in order to do this. But if I do position here, you see that I lose tangency, okay? So in order to use the match curve, I must only also understand that I need to take into account what topological changes are happening inside the curve. Now, the match curve is a command that dynamically can adjust the topology to the desired level of continuity. But there are commands that cannot do this. So you need to create the right topology in order to have Rhino adjusting the continuity to the desired level. And in that case, if you don't provide enough control points, you simply cannot adjust both continuities on both ends to the desired level because you lack the right amount of control points. Okay, so if I increase, for example, continuity set to curvature and preserve other end set to curvature as well, what I get as a result is a curve with 3 plus 3 control points, which is totally different from the curve that I had originally, which was this one with this shape and with 4 control points. Okay, so this, I repeat, the match command with curves is a command that can adjust topology dynamically in order to satisfy the continuity needs that the user has. Okay, but this is not true for all the commands. Okay, so match is another command that allows to create curvature continuity, for example, by placing the control point in the proper way. The thing is that if you want this connection here, eventually I wouldn't do this with a match, because if I want this connection, I wouldn't match a third curve between this one and this one. I will create it with this connection line with a blend, because it is adjustable. The match is not adjustable. Okay, so it simply places 3 control points in an arc shape topology, but with exactly the same curvature value in the endpoint. Okay, so if this area is more flat, then there is more separation. If this area is more curved, then there is less separation between the points. But anyway, it's automatic. If you want to create this line here, eventually you can do it with an adjustable blend curve, which gives you access to curvature continuity, but you can create also extreme connection curves like this one. They both satisfy the curvature continuity, but you can change the shape accordingly. Okay, so yeah, basically blend and match curve. This is an arc blend. Just to comment this utility, this is something that you might want to take into account if you have some, let's say, production limitation. Or if you are an architect or an engineer and you want to build something, this kind of curve, for example, is absolutely fantastic in terms of geometrical shape and simply aesthetical evaluation, right? Because it's perfectly smooth, right? But if you want to create this curve, let's say in the building site, you have lots of problems because this is an organic shape. So being an organic shape, I'm going to point it out with the analysis, the curvature analysis of this line. So I'm going to import this curve, like set one curve, and I'm going to reparameterize it and use the standard and normalized slider. So you see, this is the curvature circle, also called the osculating circle of the curve in the start point. And if I move this, being an organic shape, the real meaning of organic is simply that there is no single geometrical rule along the path of this line. There is a mathematical rule because there is one single equation, but the geometry is constantly evolving and changing. So there are no two adjacent points with the same curvature radius, for example. Okay, so in order to trace this line, for example, in the building site, well, your people should struggle a lot because you should approximate this with a discrete set of points of center, and then therefore you just will be doing some interpolation between arcs in the end. So this command here allows creating an arc blend between these two lines, for example. And you have, this is also adjustable. So let me get rid of the control point and get rid of grasshopper, and also get rid of this line temporarily. So I will create an arc blend just to see what happens. You see that we have this point here, which is defining where you want to displace the barycenter of this connection here. And also you see that there is this control over curvature. This means that you can create this blend curve, which is going to be smooth, well, not smoother, but with less curvature, of course, than the blend curve. But you have more control of this, and this is more useful in terms of production, okay? Because this is very easy. You know that you can only pick the center point here and the center point here and trace this arc and this arc, okay? So this is good for production, whatever type of production you are into, okay? While this one is extremely nicer in terms of geometrical aspect, but it's more difficult to construct. Of course, you can also approximate this blend curve with a degree to curve. You have some deformation occurring, of course, but in the end, you will get a more a curve which is more easy to represent in real life. Okay, there are some utilities. Actually, normally I tend to do some confusion, to have some confusion between Rhino and Grasshopper, because I don't remember if there are Rhino plugins or utility. But yes, I think that is something from Grasshopper that converts a NURBS curve into a polycurve made up of arcs. Yeah, I don't see it here. Um, Let me quickly go through this. No, it's not like this. Changing my curve, making it wrong. Simplify lines and arc. No. Oh, yeah. Convert curve to arcs. Yeah, it's this one. So right click on this. Select the curve that you want to convert, and you see that it is a complex command because it's changing the topology of the curve. Outputs arc. Delete inputs, no. Angle tolerance, for example. Angle tolerance means what's the difference in orientation between the original curve and the new curve. Now, of course, if you have a very fine tolerance, then you would get a curve with, I don't know if you can see it, but there are lots of control points along this line. Okay, I think you can see it from the distance, right? You see this little thing here. These are control points. And if you have several control points, it means that you have a whole bunch of arcs here. So you're making it easier, but not that easier to draw this line in real life. Okay. So eventually, I would be more generous with tolerance, and eventually I will decrease the tolerance. For example, like in this case, 0.1. So I start to have less control point. This tolerance, with respect to the angle tolerance, affects the precision by which the command is tracing a new line along the original line. So you have this kind of little variations in the shape. Okay. So if I increase this to 1, for example, you will have less control point, less arcs, but also more separation between the original line and the actual arc sequence. Okay, so let's keep it to 0.1. Let's enter. Okay, so now we have two different curves. This is the blend curve. You recognize it because it only has 6 control points, right? And here is the arc-shaped curve. I will move this away. So let's try to explode it. And you see that we have exploded this into several arcs, right? So if I take this line here, join it, well, undo the explode command and import it here, set one curve, and take a look at what happens with the curvature analysis here. You see that we change from one circle to another circle to another one, another one, another one, another one, but they are constant along the path of one single segment. Okay, so this is the difference between this blend curve and this arc curve. So you can regularize the NURBS geometry in order to make it more easy to be produced or manufactured in the real life. Okay, but of course you pay the price in terms of some deformation. Now, normally this is more I would say a compromise between the topology and the acceptable result. So as long as I take this line, place it back to its original position, which was this one, as long as I don't see any difference between these two lines, then the switching to a sequence of arc is perfect. Okay, so it's just a visual analysis. There is no general rule in order to decide between the blend and the arc shaped curve. Okay, so in this case, it's just the designer sensibility. Okay, but you can see that all of these operations that we are doing are somehow determined by some topological consideration. Okay. Um, so talking about tools that are inside this toolbar before leaving this detailed analysis and going to the geometric aspect of topological considerations. This session today is going to end basically on a deep analysis of NURBS topology. From the next session, we will be working with curves and surfaces in order to understand how to deal with topology, create the right topology, optimize the topology, edit the topology in order to achieve the desired result. Okay, but these all the things that we are seeing today are fundamental in order to work with geometry in Rhino. Okay. So I know this session is being quite intense, but I think it's absolutely important to understand this kind of concepts. So let's end our analysis inside this curve toolbar. Of course, there is also an analysis, a curvature analysis in Rhino. You don't have to eventually use Grasshopper at all if you want. So, for example, also when you are creating but let's move this away from here, and let's move this arc curve from here. So also when you are creating an adjustable blend curve, you have access to a curvature analysis tool, which is simply show curvature. And you can increase the scale of this graph here that you see. I will increase it a little in order to better see the curvature graphic, especially along the blend line. There is no, as we were drawing this NURBS curve by hand, like using a control point curve, as I told you, this is a degree 3 curve. By default, Rhino doesn't create a non-uniform knot vector. And there is no possibility to create coincident control points. So there is no way that this curve here has some internal discontinuity, right? So there is no need to analyze the curvature graph along the path of this line because the graph is going to be continuous, okay? And as well as the second curve, okay? You might have this kind of weird behavior, but the graph of this function is continuous, okay? Now, let's analyze this graph here in order to understand how it works. And I'm going to go back to position, right? Position generate a straight connection line. Straight lines have no curvature. So curvature is 0. So that's why you don't see any white graph along this line, because there is a white graph actually, but it is flat and it's coincident with a straight line, okay? In this case, you see that this area here is has more curvature, okay? And therefore, the curvature graph becomes higher. The curvature graph is designed on the convex side of the curve, as you can see. So when you have the graph appearing on one side and then on the other side, it means that the curvature has changed sign. It means that this part of the curve is concave to the right and this one to the left. So there is some inflection point here in this area. This is exactly where curvature is set to 0 in this point, okay? It means that this point is exactly the inflection point of this line, okay? Then there are these straight lines here, which represents the value of the curvature. it means that in this case, the value of the curvature is increasing, 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 and then decreasing, decreasing, right? And then there is the graph itself, which is the upper line of this graph. So even if you have this kind of vertex here or here, it doesn't mean that curvature has some discontinuity. The curvature graph is the line. So as long as the line is one single polycurve, then the curvature is continuous. The meaning of this vertex here is that G3 eventually is discontinuous in this point. Okay, not G2. G2 is continuous because it flows from here to here without interruption. It's just a change in direction. This sudden variation of direction means that the tangent to the graph curvature is discontinuous. So it means the derivative of the graph function, which is basically G3 in our case. Okay, but anyway, we must consider the blend curve. So the blend curve is actually showing no curvature graph because it's flat. If I increase to tangency, what happens? It happens that the curvature graph is discontinuous because there is a jump from a value that lies here to a value that lies on the opposite side. So a total change of sign, not only a discontinuous value, it's a total change of sign. Okay, this means that this curve has some curvature oriented to the left, while this one has some curvature oriented to the left, to the right. Sorry. Okay, remember that the curvature graph appears on the convex side of the curve. So there is a total jump in the value and in the sign of curvature in this point. Curvature discontinuity, right? When there is tangency, the so-called hair, which are basically these lines here, the hair are on the same direction because the curves are tangent. The hair are perpendicular to the path of the lines of the curve. Therefore, if there is tangency continuity, the perpendicular to the endpoint of this one is exactly the same perpendicular to the blend curve in this point here. So they are aligned, okay? When there is discontinuity and there is only G0, you see that the curvature graph takes two different directions, okay? So this is very useful to understand. You get many information from the curvature graph, okay? Not only what's the amount of curvature, not in value, of course, but in intensity, at least. But you also have information about the continuity, the real continuity happening in several points. If I switch to tangency, you see that we have the same situation here. Hairs become collinear, and you only have a jump in the value and sign of curvature. When you switch to curvature, for example, curvature in 2, you see that the curvature graph becomes continuous, okay? Flows like this, but it is continuous, right? While it is still discontinuous here. If I switch to curvature, I have a continuous graph, curvature graph. Now, in order to understand what is G3, you see that many consideration happens along the way. But anyway, G3 in point 2, for example, what will it do? If I want my blend curve to be G3 continuous, I must avoid discontinuities in curvature graph. So if I set this to G3, take a look at the curvature graph, it becomes smooth, right? Of course, we are adding an additional control points, no longer 3 control points, but 4. And this allows to better take care of the smoothness of the curve in the first part. So this is avoiding, for example, that this curve can eventually have some curvature, well, according to the direction that I am flowing in, some curvature to the left before turning to the right. This will be a visible curvature, well, not discontinuity, but variation, right? So in order to avoid this, if I set this to G3, an additional control point is added, which is in this case aligned along the direction, and this avoids a correction in the direction of the curve. So it avoids oscillation, right? This, if I am not wrong, is it called with a funny word in English? It is called the jerk. Okay, so the jerk in this case is not a bad word. It's just the way that the third derivative is called, right? So G3 continuity is jerk continuity. Sorry, but that's the way it's called. And then there is, for example, just because you can see it here in G4, um, this means that G4 is basically a discontinuity in the variation of the jerk. The variation of jerk is called pop or crack. Okay, so you see, this is more like a sound um, thing. Okay, so for example, pop, crack is something that happens very, very fast, right? So a G4 discontinuity means that along the curvature or along the path, you have extremely sudden variation in the path of the curve. So if the jerk is an oscillation, the pop or crack should be something like a vibration, right? So it's something that it becomes very difficult to interpret in a geometrical way. But that's why, for example, I also wrote it on the book, but let's say discontinuities higher than the pop or crack are also difficult to imagine, like with a geometrical representation. So they are not even taken into account, right? So you can go as deep as the G4 if you want, but it has a very, very, very specific meaning that normally you don't take it into account in a normal workflow, okay? But anyway, in this moment, you also got an explanation of the G3 continuity. And G4, you can see, for example, also graphically, you only get an additional control point, more or less aligned, but this is simply making the curvature graph smoother and smoother, okay? We tend to maintain our considerations up to the curvature graph, okay? Because this is basically the geometric aspect that we can easily understand and clearly represent in our projects. All right. So think about the G3, G4 like refining the curvature, if you want. Okay.
Giancarlo, how do
Yeah.
you increase the size of the curvature graph?
You can't.
Because
I mean, in this moment, you can't. This is something that it's happening automatically. If you want, you can tweak the position of the control points. In that case, for example, if I let's disable the snaps here. If I see that this curvature tends to go to the left according to the direction that I am flowing in right now, if I move this away, eventually this curve will tend to the left more, and then this part of the graph is result in a more evident curve, or let's say it's simplified somehow, right? But this is something that it has to deal with the shape of the curve simply. So for example, let's move away from this graph here. If I take a curve and tend to place the points in a smooth flavor like this, or I do something like, I don't know, something like this, and suddenly I create a very small curves here on top, and I analyze the curvature of these two lines here. Of course, I will do this in Rhino without going to use, oh, sorry, I took the curvature analysis. No, I need the curvature graph. Okay, so in this case, you see that I obtained this kind of amplified version of the graph because I created a simply more curvature in this area. You cannot edit this graph. This graph is just a visual representation of the curvature of your curve. You cannot work on the graph, you can work on the curve. So if I take these points here, if I move it away, I am creating a sharper part in this area, and then the graph increases its size. But you cannot do this directly. You have to edit the shape of the curve. Okay?
I mean, right now, I don't know, I might doing something wrong because I have the curvature graph that is really close by the curve, and the curve is really similar to your.
Yeah, but there is also a display scale, right? So if you decrease the scale, you get this. If you increase the scale, remember that this is giving you no numerical information, right? This is only telling you what's the variation, what's the behavior of the curvature along the path of the curve. But therefore you have this scale factor here. So if your graph is basically sticking to the curve, even if your curve is complex like this, then you might want to increase the display scale in order to have this kind of representation, which is clearly better for
Yeah,
understanding.
yeah, that was
Yeah.
because it was 111 and I should put 220, and now I have
Yeah,
it.
also consider that it depends also on the scale of your drawing, right? So this display scale might be good for a curve drawn at a specific scale, and simply not be good enough for another drawing that you did. So it depends on the geometry that you are creating, okay? But you simply
Absolutely.
have to tweak this.
Yeah.
Um, Okay, so I won't go in detail about the curvature graph in Rhino. It's very simple to use it. But the important thing, for example, is that you can visualize it during the blend curve execution, which is something that it's useful to understand what you are doing in terms of continuity, okay, between the blend curve and the original curves that you are using. Um, so yeah, that's pretty it for the blend. And now let's go to the let's say let's say the in between the topology and the geometrical aspect. Okay, let's start to um, optimize something or deal with standard noobs topology when you're inside a usual Rhino workflow. Okay. The last thing about topology that I'm going to tell you is just related to one of these utility that we have here, which are fit, degree, and fair. I will not deal with fit and fair, which are basically secondary with respect to other comments, which are basically the rebuild comments that we are going to discuss in detail. But I'm going to show you the degree, because this is a common error. People think that as soon as they realize that the degree is important, they try to change the degree of a curve. Now, this is a one-way road, okay? So if I, for example, create a curve, NURBS curve with degree 2, okay? And I create this line here. And I take this line and change the degree, which is actually 2, and change it to 3, and hit enter. You see that we have a different topology, not only because of the degree, of course, because it has changed to 3, but also for the amount of control point. Different topology, but the same shape. So you see, if I undo and redo, you see that changes the topology, but not the shape of the curve, right? So when you change the degree, increasing the value of the degree, you can do this without risk, because the curve is not going to change the shape. If I take this curve, repeat the change degree, and I want to edit this curve in a smoother way. So the reason why we might want to do this is because we want to change the shape of this curve and change it smoothly, right? So we have now a degree 3 curve, which means that if I have this dense concentration of control point, it means that if I take this point and move it, I am affecting only this area of the curve, because eventually this point is directly changing the shape in this span, also in the previous and next span, but more lightly, right? So with degree 3, we have a more strict relationship between the control point and the span that the control point affects, right? So the reason why I might want to increase the degree is because I want to produce a smoother deformation by changing the position of one control point. Now, this might seem a good idea, okay? But if I change the degree of this curve and I switch to 5, it's true that I maintain the shape of the curve, but I no longer have only 4 control points here. So I increase also the number of control points, which means that if I take this point here and move it, I have the same, exactly the same behavior, because I also have more control points. Remember that increasing the degree means that I also increase the number of control points, because I am maintaining, in this case, the number of nodes and the number of spans. So if the number of nodes and spans doesn't change, and I increase the degree, it means that I must have more control points, but they will affect the same span due to the increase of degree. So we have, let's look at this with a new control point curve with degree 2. Okay, I am creating this single span degree 2 curves with 3 control points. Okay, it means it only has one knot here and one knot here, one single span. Now I can take this, copy it, change the degree, and set it to 3. Now I have one single span with 4 control points, right? If I do this and change the degree of this to 5, now I have one single span with six control points, right? So change the degree means only change the degree of the curve. It doesn't affect the knot vector. So if the knot vector stays untouched, it means that if we have one span, we will always have the corresponding span. But if we have one span and we have degree 5, we need 6 control points to affect that span. So change in the degree, increasing the degree, of course, increases the number of control points that affects one single span. So the deformation will always be local, okay? The problem of local deformability is strictly connected to the topology of a curve. So if I want to change the shape of a curve more smoothly, I don't increase the degree, okay? I decrease the degree. Because if I decrease the degree, what happens is that one control point will affect more, a larger portion of the curve. So if I increase the degree, I don't change the shape, which is something that, from an intuitive point of view, it's what any designer would do. I want to change complexity, increase complexity without changing the shape of the curve. But if I do it by changing the degree, it's true that I don't change the shape, but I create a more complex topology where I don't get any advantage in terms of smooth editing, because I increase the degree, which corresponds to a smoother aspect, as we saw here, for example, okay? But I also increase the number of control points, which leads back to a local deformability. So if I have a control point curve and I want smoother deformability, I must do so that one control point affects a larger portion of the curve, which means that I must increase the size of the spans, okay? So I must decrease the degree. And why is the degree change a one-way road? Because if I change the degree, decreasing it from 5 to 3, you see that I have now reduced the amount of control points by changing from 5 to 3. But the degree 5 curve had lots of control points, okay? You see that here, I have lots and fewer control points. Now, when I decrease the amount of control points, I change the shape of the curve. And I am also changing the degree, so there is some deformation occurring. So if I do this change of degree in a curve which has a very complex topology, I can also, let's say, I can also discard basically the deformation that is occurring, because there is a dense population of control points. But if, for example, I have a degree 5 curve, like this one, with few control points, and also with an irregular distribution, like this one, if I change the degree of this curve by decreasing it to 3, then in this case, I have a very important deformation occurring, okay? So when you want to change the degree of a curve, take into account that if you change the degree by increasing the value, you have no deformation. You are creating a more complex topology, but there is no deformation for the curve. Okay. So you can increase the degree in order to, let's say, create, basically I would do this between degree 2 and degree 3. I wouldn't do this with a higher degree curve, for example, from 3 to 5. Remember to skip even numbers, okay? So from 3 to 5, I wouldn't do this because we get the result that we got here, okay? So if I change the degree of this and set it to 5, I increment the amount of control points. I still have local deformability. Eventually, if I want smooth deformability for this curve, I would have to delete some control point, okay? Because if I don't delete control point, I still have local deformability. Deleting a control point means basically deleting a knot, okay? So if I delete a knot, I make spans more wide, basically. So one control point will affect a wider portion of my curve, okay? So this would be eventually a process. But as we are willing always to work with a maximum of degree 3, this is something that is not recommendable. And on the other hand, when usually you don't have a degree 5 curve with this kind of complexity. Eventually, you work with a degree 5 curve with a smoother aspect, which means few control points. In this case, you don't want to decrease the degree of a curve. Okay, so change of degree is something which is very delicate. You don't want to mess with it, because if you do this, you get a very radical deformation of your geometry, and eventually you have to start from scratch in order to create the proper aspect of your geometry, right? So we are working in quite an abstract way right now, because we don't have any relevant design, okay? But keep in mind that if you want to increase or decrease or change in general the degree of a curve, this is something that I wouldn't recommend at all, okay? Especially if, as an independent operation, okay? We will see that in the next section, we will see that there are commands that allow changing the degree, but in a more controlled environment, okay? So in that case, it is absolutely recommendable to try experimenting in changing the topology of a curve, but in a controlled environment, not like this one. Fair and fit, just to name them, they allow let's say, changing the topology of a curve, keeping the curvature normally under control. So fairing of a curve is something that it's very important, for example, when you want to make one geometry easier to manufacture, okay? So for example, fair means like make a geometry more gentle, more elegant, right? So this is general meaning, but fairing in terms of topological control means avoiding, like, well, we can express it like avoiding the G3 discontinuities or G3 variation. So avoid the jerk phenomenon, like the curve starting to dance around and oscillate around. So fairing tends to eliminate this kind of oscillation and make a curve more easy to manufacture, more aerodynamic, more smooth, and so on, okay? But this is something that we are not going to discuss, because these are very problematic commands. If you find yourself using the fair commands, it means that you did something wrong before using it, okay? So I do prefer to have a let's say linear approach to topological control in order to create directly the desired topology and the desired shape of the curves, okay? And fit, we will discuss fit inside other commands, because also, like the degree is something that you might want to tweak, but in a controlled environment, okay? So we will discuss fitting of a curve or a geometry in general inside a controlled environment, where we can take and keep under control the effect of fitting the geometries, okay? So, okay, so that's it for now. Do you have doubts, questions? Do you want to further discuss something, I'm available.
Giancarlo, regarding the NURBS not uniformal command that it was in the beginning.
Yeah.
I mean, can you recap it? Because I remember that it changed the power of the point, and it was when you were changing from 1 to 2 that suddenly it became uniform. But how is that?
No. Rational, not uniform.
Ah, all right. So
Rational.
it might be that.
Rational. So for example, if you have this curve here, oh, sorry, this is degree 5. If you have this curve here, okay, and you take one of well, and you take a look at the description here in Rhino, it says that it is non-rational, okay, but it is uniform. Uniform has to deal with the knot vector. Rational or non-rational has to deal with the control points. Non-rational means that all the control points have the same weight. Okay, so you can also take, for example, all these control point here, go in the point editing toolbar, take the control point weight command, and say, for example, that you don't want 1 to be the weight of the control point, you want them to be 2. Okay, you see that nothing changes because you are increasing the power of all the magnets, right? So there is no change in shape. This curve, if we go into details, is still non-rational because all the control points have the same weight. But if I take, for example, just one of them, like this one, for example, just one of them, and edit the control point weight and increase it, I can obtain this kind of very sharp corner here, and this curve has become rational. Okay? So rational has to deal with the weight of the control point, which is part of the NURBS equation. Okay, so the weight of the control points can make the curve become rational. If you work with the same weight for all the control points, you have a non-rational curve. But remember that this is a possibility that you can consider when creating your design. Because as you can see, for example, one thing that eventually you might want to do, instead of increasing the amount of control point to deform the shape of the curve in a particular spot, you might want to increase the weight of that control point that lies in that area in order to pull the curve stronger and create some kind of, let's say, more sharp behavior, right? But remember that this is very good if you're still working Rhino and you don't exit Rhino. But if you exit Rhino, it's easier that the software that will receive the geometry will not be able to work with non-rational curves. So you must prefer to work with a interoperability workflow. So I wouldn't recommend to work with weight too much.
Okay, that was it. And regarding the NURBS equation, or maybe other equation that we are discussing, will it be possible to have it in the script, in Grasshopper script, or in the Rhino scene if you're sharing that? Because I know that is not the topic that you're saying, but it would be nice at least to read it and know what's the equation.
Yes, look, if you want to take a look at the equation, you can go to, if I don't remember, I think it was Wikipedia or something that has a nice description. Actually, you can see it. We can take a look at this. NURBS equation with non-uniformity of the spline. I think there is a quite a good description here of this. Well, this is it. This is the general form. This is the general equation. There is also a compact version, which is this one. When you substitute with R, you substitute all this part here, which is basically this. So you see that, for example, in this case, you see this W. W are the weights of the control points, right? So key is the amount of control points. So for each control point, you are taking into account the one thing that is called the basis function, okay? And you are taking into account the weight of the control points. So when you change this, when you don't change the weight of the control points in Rhino, Rhino assumes that you are working with an equal value for the control points weight, right? So it means that WE and WE are basically the same value. So they don't affect the equation, right? So that's why when you increase, for example, from 1 to 2, all the weights of the control points, it's simply 2 by 2, and they simply go away, right? So they don't affect the shape of the curve. That's why the shape of the curve remains untouched when you increase or decrease or change all the weights of the control points. But if you change one weight for one control point, then this will become different, because this is a polynomial equation, right? So it's basically a sum of several elements. And there will be one element with a different value for the weight of the control points, okay? Sorry, I was discussing this one, but actually it's this one, okay? So if you change the control point, the weight of one point, you will affect only one part of the equation. If you change the weight of all the control points, this value will be the same as this one, and they don't affect the final equation, right? So that's the meaning of the weight.
And the other equation we were discussing in the beginning regarding the degree of the curves.
Oh, the relation between the degree, the number of control points, and the knot vector.
Yes.
Yeah. I can share it if you want. I want to be sure that I share the exact formula. So let me go here a while. Please be patient. I'm going here and here and here, and eventually, it was, let me go, I should have the divided by chapter. Yes, this is chapter 1, maybe, or this is an extract, I don't remember. Sorry, let me double check, but, oh no, this is already advanced stuff. Let me see if I have it on one single. Well, I prefer to go into the translations here in English, and it should be somewhere like here. Okay, I'm going to find it here. This is the final edit before the printing, but let me decrease this so I can clearly find it. I think it's chapter 4 or something like that. This is curvature analysis. Yeah, it's Nernst geometry. So this is it. Okay, this is the equation, and this is the order explanation. This is curvature, change in degree, knot vector. Yeah, it's this. So it's this one. The number of values in the knot vector is equal to the degree plus the number of control point minus 1. Yeah, so I was saying this correctly during the explanation. So you take the degree, add the number of control points, subtract 1, and you know how many values you must have in your knot vector. Okay. So if you want, we can do this with a generic curve. The most effective exercise that you must do if you want to be sure that you understood this thing of the knot vector is basically create a control point curve from scratch in Grasshopper. Okay? Because Rhino doesn't allow to do this. Okay, so you can do this in Grasshopper by taking a point container, set multiple points, like for example. A random set of control points. I don't even know what's the amount of control points right now, no? And I don't want to count them. I only want to count them right now that I have in Grasshopper. So I take a list length, and I know that I have, in this case, 12 control points available, right? So the thing that you must do if you want to be sure that you understood everything is this one. You create a curve, a NURBS curve, not with a, sorry, a spline, not with a standard NURBS curve, but with a NURBS curve PW key. okay, which is based on points, weights, and knots. So this forces you to define a knots vector. So you take this, and if you are correct, then you know that you want to create a degree 3 curves. So 3 plus 12 control points is 15, and you need 14 values for the knots. Okay, so you go here and you create a gene pool, which is the more efficient way if you don't want to work with a complex sets of sliders. This is basically one single set of sliders. You edit this, and let's get rid of the decimals because they are not necessary, because remember that Grasshopper always generates the normalized knot vector, okay? So we only need to define how many genes, and we need 14 in our case, because it was 3 plus 12 minus 1, 14 genes, 14 sliders. We only need to define properly the minimum is set to 0, and it's perfectly fine, but the maximum, okay? So how do we define the maximum value? We must have 14 values, okay? But we are working with a degree 3 curve. So if you want the degree 3 curve to start from the start point and finish in the end point, the first knot and the last knot must have full multiplicity. It means that 3 values plus 3 values are going to have the same value. One will be 3 zeros, and one will be 3 times the higher the maximum value of this range. So we must have 14 values, which means minus 3 for the full multiplicity initial knot, which is leaves us with 11 values. Minus 3 for the last knot leaves us with 8 values. These 8 values will be the changing numbers in the inner part of the knot vector. And we want to create a uniform knot vector. So it's going to be like 1, 2, 3, 4, 5, 6, 7, and 8. So the first value will be 3, 0. Then you will have 8 values, which will be from 1 to 8. So the maximum here will be 9. Okay? So once you do this, you will have your knot vector ready for being customized and plugged into knots. And you will see that if you take 0, 0, 0, and then 9, 9, 9, and then you have 1, 1, 1, 2, 3, 4, 5, 6, 7, and 8. Here is your NURBS curve. Any edit you do in this knot vector will create a non-uniform non-uniform, non-rational basis spline in this case. Non-uniform because if you change something here, the knot vector is non-uniform, and non-rational because the weight of the control points is all set to the standard value, which is 1. So in this case, for example, if you want a non-rational uniform, non-uniform rational B-spline, you must provide a weight, a specific weight for each of these points. So if I take, for example, I don't know, I want to create a standard weight like 1, and then I want a different weight like 2, for example. And then I'm going to repeat this value here. Repeat it like the same length of this amount of control points, but minus 1. So basically I have 12 control points. 11 of them will have the same weight, which is 1. And then I will have this value here, okay? So I am creating a set of weights, all the same, all 1, but one of them which will have the weight of 2. So I'm going to create, for example, a jitter component here. In order to take all of these values here, I'm going to flatten them in order to have one single list of values. And I'm going to take these values here and basically shuffle them. So in order to shuffle them randomly, I need to specify also a seed, like, I don't know, something like this. Okay, and so I should have something like changing the position of the two, as you see, when I change the seed, okay? And if I take this, I will have a point with weight 2 moving along this curve randomly, okay? So now I have a non-uniform, because the knot vector is non-uniform because of this double knot that I have here, the 3, and it's rational because I have not the same weight for all the control points, okay? So this is what you must do if you want to understand, if you want to make sure that you understood exactly all these non-uniform and non-rational or rational stuff, okay?
Fantastic. Uh, and if you use the normal NURBS curve, the nodes are generated automatically.
Yes, exactly.
Okay.
Exactly.
Yeah.
Because it takes into, you see that the NURBS curve is generated starting from vertices, which are the number of control points and the degree. So once you know how many control points you have, and you know what's the degree, via the formula that we just saw, which is number of control point plus degree minus 1, Grasshopper knows and Rhino knows how many knots you have, and by default, it generates a uniform knot vector with full multiplicity for the first one and the last one. So there is no other way of creating a knot vector. While in this case, the curve is based on the amount of control points and the knots, okay? So the degree is not even taken into account because by default it's 3, okay?
And as last, something that is not completely connected, but is connected with the previous course, that is Kangaroo, is just a curiosity. The discretizations process in Kangaroo, because we always have to input a curve that is shattered.
Yeah.
Does it have, I mean, why is like that? Why Kangaroo cannot work with a NURBS curve, for example? Why do we have to split in different parts? I know that is something not related with that, but I mean, now
yeah,
that
actually, it has nothing to do with topology in that case. The problem is that well, you know, this is something that you might want to explore in the recording of the webinars on textile simulation, because it has to do with the schematic representation of elastic body, especially with springs representation. So basically, it depends on the fact that Kangaroo is based on the ideal spring. And I think you had some physics in your curriculum, right, in your study. But if you consider, for example, a real spring, which is something like this, well, sorry for the, the drawing, but if you consider this, it's true that this spring can basically contract and expand in this direction. But it's also true that if the wire is thin enough, you can also bend the spring like this, okay? Now, if you consider the bending problem inside the elastic simulation, you have a very, very complex differential problem, right? So Kangaroo is based on a schematic approximation of the spring, which is called the ideal spring, that cannot bend. It can only stretch along the longitudinal axis. And therefore, Kangaroo can only work with linear springs, so straight lines. Okay, so when you need to convert a line, whatever line, into an elastic cord, for example, you must shatter it into segments and also provide linear segments. So you cannot work with a NURBS curve. You must take this line and eventually approximate it with a polyline, and each segment of the polyline can become a spring, not the curve. So it's just the way that the elastic problem is translated into an approximation via the ideal springs, okay? So it has nothing to do with topology. And the way you do it, of course, is by shattering the straight segments or converting a NURBS line, a NURBS curve into a polyline and using the segments and so on.
Perfect. I was thinking there was some kind of relation, but that's perfect. Good to know.